Optical antenna. A 4 inches diameter lens with a focal length of 50 centimeters is used. The truncation ratio is approximately 0.88, and the lens Rayleigh range is approximately 5 kilometers, which means that the laser beam can be collimated for all desired range, 100 meters to 4 kilometers. This lens is mounted on an aluminum rail with a fiber holder that houses the optical fiber. A 6 inches mirror is also mounted on the same rail to steer the laser beam, and the entire setup is mounted on an optical table. Balance detector. An in-gauze heterodyne balance detector with a bandwidth extending from DC to 125 MHz is used to retrieve backscattered signals. The benefit of using a balance detector is to subtract the two optical input signals from each other, which results in the cancellation of common mode noise. This allows for detection of small changes in the signal path from the interfering noise floor. The photocurrent is converted into voltage through the detector's transimpedance amplifier module. Detector's noise was measured using a spectrum analyzer while no optical signals were applied to its inputs, gain was set to 1 times, transimpedance was set to 1.4 kiloohms, coupling was set to DC, and spectrum analyzer's frequency resolution was set to 3 MHz. Detector's noise was equal to -83 dBm, which is 1 decibel below detector's specification of 3.6 pWHC-half. The detector has a non-flat gain response, i.e. the gain of the detector varies with the frequency of the input signals. Non-flat gain response of the heterodyne balance detector. To correct for this non-flat gain shape, received signal's power spectrum is divided by the power spectrum of detector's output while no signal is present. The measured power when signal is present can be represented as dividing this measured power spectrum by the power spectrum where no signal is present gives, where SNR is the signal to noise ratio. Subtracting 1 from 16 gives the SNR. The previous technique is used in our signal processing to estimate backscattered signal power.